Hey physics students, welcome back to another edition of Rapid Review for Honors Physics. Today we're going to talk about the graphical representation of vectors. We're beginning to ease into the topic of vectors. We've used vectors all along because, as you know, velocity and position and acceleration are all vectors. We've been doing them mostly in one dimension. We're beginning now in this course to move towards 2 dimensions, and we're going to use arrows sometimes to represent a vector graphically. Take a look at this picture. Here's a person throwing a ball up. There's a ton of information in this picture. We're showing 5 different moments in time. The position is either there, or there, or there, or there, or there, and we're talking about different elements of its motion. So the displacement is evident from the picture. The velocity is indicated by a blue arrow, which describes how fast it's going by its length. And the direction it's moving, by the way, is pointing. And that is the convention for vectors. If you're going to draw a vector with an arrowhead, and you want to be careful about the graphical representation, you would let the length represent the magnitude of the vector, how big it is, and you would let the direction be the direction of the arrowhead. Okay, so those are the conventions for vectors, what I just said here, and that works for all vectors, not just velocity vectors that we see here in this diagram. Here's another artist who chose to draw this up and down problem as shown here, and you can see that this artist has everything moving in one line up and the same line down. So on the path down, the ball might be in the same position as it was on the way up, except it's moving and it's just obscuring the picture of the ball from the trip up. So it's really just an artist's decision. You probably noticed in this earlier picture, the artist chose to nudge the trip down over to the right a little bit so you could see everything in one picture. Importantly, we're talking about motion in one dimension right now, so we don't have any left to right motion. And so that's just a graphical convenience, but not precisely accurate picture. All right, so let's look at a 2-dimensional version now. So 2 dimensions allows us to talk about motion, say, for example, on a road. So here's a picture of a car driving on a road. We see several different positions of the car at different moments in time, and the arrow, the green arrow, represents its vector magnitude and direction. So at first, it looks like the car is going south and a little bit west, and by the time we get to the middle of the curve, it looks like the car is heading straight south. I can tell from the size of that vector arrow that it's slowed down for the curve because the magnitude of that arrow is not the same as the magnitude of when it started out. So that's how we use vector arrows in 2-dimensional space. Okay, so totally fine to do that. We're in 2 dimensions now. We'll show, anytime we want to show a vector, we'll show it as an arrowhead. And we will, in most cases, be careful to have the length represent the magnitude of the vector and the arrowhead, the direction. I say in most cases because we're going to see later that might be inconvenient later, but as we're understanding the meaning of vectors and vector arrows, we will be careful to try to do that as best as possible. What trips us up, though, is that the units of acceleration and the units of velocity and the units of displacement are different from each other. So if you come up with a textbook like this one that draws a figure where they combine acceleration vectors and velocity vectors into one diagram, just be careful you can't compare magnitudes of an acceleration vector to magnitudes of a velocity vector. There's an implied scale in that picture, which in this textbook was not provided. So just be careful with that. You'll see this kind of notation frequently. It's just meant to be a conceptual help, not a precise measurement of everything. By the way, the acceleration vector in that slide came from, or the entire slide came from this textbook. This is Halliday and Resnick Physics. This is an earlier edition. The current edition, they're up to edition 12 by now. And I highly recommend this. You may actually even use this in college. It does use calculus, which is why we're not using it in our honors physics class now. Let's see, I think we've probably said all we need to say about this. Let's see if we've got any more slides. Oh yes, graphical vector addition. So you will hear of tip-to-tail method and parallelogram method. You may have even done some of this in class. I am not going to cover that in this course or in this review. If you want to learn, there's tons of stuff online about it. And I, in this class, will be jumping more to quantitative measurements that don't depend on accurate drawing. So if you're interested in graphical vector addition and the concept of adding vectors and what it means to add a vector in 2 dimensions, check that out. You can look up these keywords, tip-to-tail method and parallelogram method. That's all I have to say about arrows for vectors. Join me next time.